Hey everyone, Ms. Hogerman here. I'm going to show you a few examples of Hardy-Weinberg equilibrium problems so that you kind of know what to expect and so you understand kind of how I go about attacking these problems, and hopefully some of this helps you in addition to what Mr. Anderson taught you. It's going to be really helpful for you if you have a sheet of paper out and your calculator ready. I have my calculator ready right in front of me as well. You don't need a fancy calculator, just one that will allow you to do square roots is really all you need, and even very simple 99-cent store calculators have that. Okay, so before we get into this problem that we see above us, I just want to remind you of all of the variables in this problem. We have two formulas. We have p squared plus 2pq plus q squared equals 1. And remember, the p squared is just the frequency. And remember, whenever we write frequencies, we are going to use decimal points. Okay, now they may be represented as percentages as well, but we're always going to convert a percentage into a decimal point. So if it says something like 30% of the population has this, that would be a frequency of 0.3. So you just move the decimal place over. Okay, anyways, if this is our first equation here, p squared is the frequency of individuals, so like actual organisms, like tigers, in our population that are homozygous dominant. So it's like the percentage or the frequency with a decimal point of how many individuals are big R, big R. Now, our 2pq is how many individuals are big R, little r in our population. And our q squared is how many individuals are little r in our population. Now, when it comes down to it, in any given problem, you're really only going to know the phenotypes of individuals in that population. You're not necessarily going to know their genotypes, okay? Especially if they're dominant. So in our problem above, it says that we have white tigers are recessive, and we're going to assume that the normal orange tigers are dominant. Well, that means that orange tigers could be big R or big R little r. And so if we look at the problem that we have on the screen, calculate the expected number of heterozygous and homozygous dominant individuals in a population of 10,000 tigers if 10 are white, well, that means 9,990 of those tigers are orange, and they're either homozygous dominant or heterozygous. We don't know, kind of like when we used to do those test cross problems. What we do know is that 10 of those tigers are white. And so if 10 of those tigers are white, we know that white is recessive. The only way they can be recessive is to be little r. So realistically, what we know is q squared. And we're always going to start off by figuring out q squared. That's what I always want you to do. Okay, I have to erase a whole bunch of stuff, so just be patient with me. All right, so first step, calculating our q squared. Well, right now, like I said before, q squared must be a decimal point, but we don't have any decimal points in this problem. So instead, what we're going to do is we're going to make these numbers into a decimal point. We have 10 tigers, and we have a total population of 10,000. So if we do 10 divided by 10,000, we're going to get that frequency. That's literally all you do. You take the number of the trait you want divided by the total number of alleles in that population, and or individuals in that population in this case, and you end up with that frequency. So in my calculator, and I want you all to do this so that you make sure you're plugging in your numbers correctly, I'm just doing 10 divided by 10,000. So I type in 10 first, then the divide symbol, then 10,000. And when I do this, I get 0.001. If you don't get that number, please keep trying plugging things in until you get that. This is my frequency of q squared. This is how often my homozygous recessive genotype shows up. Well, now that I have q squared, I can actually figure out anything else that I need. Now remember, ultimately what I'm looking for is the number of heterozygous individuals, so that's 2pq, and I'm also looking for how many homozygous dominant individuals, that's p squared. Right now all I have is q squared. So what I have to do is I actually have to solve to find p, and then I can find anything. If you remember from the Bozeman videos and from my PowerPoint, we have this other formula, p plus q equals 1. That means that in a population, 100% of the alleles are accounted for by dominant alleles and recessive alleles. So p is the frequency of dominant alleles and q is the frequency of recessive alleles. Well, if I have q squared, which of those two variables can I find? That's pretty easy. It's actually just q. So here's how you do that. We take our q squared, which was 0.001, and if we want to find q, all we have to do is take the square root of that q squared. So really all we're doing is the square root of 0.001. Now, I want you to try this in your calculator. You need to hit the square root button, and then you need to type in 0.001. When I do that, I get 0.032, and you're welcome to round to the 100th or 1000th place. It's up to you. Well, now that I have my q and I have the number 1, it's really easy to solve for p. You just subtract q. That means p equals 1 minus q. Well, if we calculate that, we have that p equals 1 minus 0.032. And so if we subtract that on our calculator, or we actually go 1 minus 0.032, we end up with a p-value of 0.968. Now we have both q and p. We can solve for everything else we need. So pardon me while I erase a couple more things. Thank you for your patience with me. So I'm going to just rewrite this. We have q equals 0.032, and we have p equals 0.968. Now remember, in the problem, so read the problem above while I'm erasing, it says that we are expected to calculate the number of heterozygous individuals, which is 2pq, and we're expected to calculate the number of homozygous dominant individuals, which is p squared. Now that we have a q value and we have a p value, we can easily solve for these. So what we do is we do 2 times our p, which is 0.968, times, and that's a decimal point right there, our q value, which is 0.032. When we do that, we get, and I'm literally typing this into my calculator right now, which is what you all should be doing, we get 0.062. That's our frequency of heterozygotes. That's not our expected number yet, by the way. If you want to find the expected number, you have to multiply that by the total number of tigers in the population, and we'll get there in a second. Now for p squared, all you're going to do is you're going to multiply your p number, so that would be 0.968, and you can either square it if you know how to do that in your calculator, or if you have a really simple calculator, you can do what I do and just multiply them by each other, because that's how you get a squared. So I'm just typing in 0.968 times 0.968, and I get 0.937. So once again, those are my frequencies. In this problem, it's asking for the expected numbers though. So all we do from here is we just multiply the decimal points that we have times the total number of tigers. So if I want to find out the number of individuals that are that are heterozygous, I do my 2pq number, which was this. I do 0.062 times the total number of tigers I have, which was 10,000. And don't forget, we're all practicing typing this into our calculator right now. So you have 0.062 times 10,000, and you get that there are 620 heterozygous tigers. As far as our homozygous dominant tigers, we multiply our p-squared number, because remember, p-squared is the frequency of homozygous dominance. So that's 0.937, and we multiply that times our amount of tigers. So multiply that in your calculator, and you should get 9,370 tigers. So since this is what the problem is asking for specifically, I want you to either put a box around your numbers or circle them or something to show me that those are your concluded values. Essentially, what we have done just now is we figured out that every tiger that is not white is either heterozygous or homozygous dominant. We have to calculate it this way though, because we're not sure of those extra tigers which ones are homozygous dominant or heterozygous without separating them with the Hardy-Weinberg equation. So if you add up these numbers plus the 10, you should get something really close to your 10,000 tigers. It might be a little bit off, but that's because of rounding error. So don't worry too much as long as your numbers are very close to the total number in the population. All right, I hope this helped, and I'm going to go ahead and record another practice problem next.